This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2017 AP Calculus exam, free response question AB3 BC3, namely the fundamental theorem of calculus. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I am a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by discussing some background information associated with the fundamental theorem of calculus. Then I'll present some information to help discover, interpret, and visualize the FTC Part 1. I'll talk about the FTC Part 1 and present some examples, and then I'll do the same with the FTC Part 2. And then I'll apply the fundamental theorem of calculus, or really rewrite the conclusion, as the net change theorem. This is an often tested concept in AP Calculus. And finally, I'll leave you with a few more good examples. The fundamental theorem of calculus is the most important idea in calculus. It's mentioned clearly in the curriculum framework as part of Big Idea 3, Integrals and the Fundamental Theorem of Calculus. The FTC establishes a connection between the two branches of calculus, differential calculus and integral calculus. It gives us this precise inverse relationship between the derivative and the integral. And the FTC allows us to compute many definite integrals very easily without going back to definition and using Riemann sums. Here's a little bit more background. The fundamental theorem of calculus Part 1 deals with functions that are defined by an equation of the form g of x is the integral from a to x of f of t dt, where f is a continuous function on a to b and x varies between a and b. Now, notice that this function g depends only on x, the upper limit of the integral. If x happens to be fixed, well, then the integral is a definite number. But as x varies, that number, the integral from a to x of f of t dt, also varies. And therefore it seems reasonable that this defines a function of x and will denote it g of x. If f happens to be a positive function, then g of x can be interpreted as the area under the graph of f above the x-axis from a to x, where x can vary from a to b. In this context, I've always thought of this function g as an area so far function. It's the area under the graph of f from a up to x. And here's a visualization. The area of that shaded region represents the value g of x. There are lots of AP Calculus exam questions that involve this concept of the area so far function. Most of these problems involve line segments and half circles. But it would be nice to have a formula or some closed form expression for this area so far function. And there are lots of standard exercises in which you can discover that g prime is equal to f. We can also realize the same result by evaluating the area so far function at two special values. First, note that the area of the shaded region is equal to g of x plus h minus g of x. This area is approximately equal to the area of the rectangle with width h and height f of x. If we divide both sides of this expression by h, the left side is a recognizable difference quotient. And if we take the limit as h goes to 0, that's the derivative g prime of x. Here's a formal statement of the fundamental theorem of calculus Part 1. If f is a continuous function on the closed interval ab, then the function g defined by g of x, which is equal to the integral from a to x of f of t dt, is continuous on the closed interval a to b, and it's differentiable on the open interval ab. And most importantly, the derivative g prime of x is equal to f of x. Here's a closer look at the FTC Part 1. Here's how I might state this result in words. The derivative of the definite integral with respect to its upper limit is the integrand evaluated at the upper limit. And here's some other notation for this result. The derivative of that function defined by an integral is f of x. Let's try a couple of examples in which we need to apply this fundamental theorem of calculus part 1. Let's see if we can find the derivative of each function. In part A, to find g prime of x, I need to take the derivative of that integral expression. The upper limit is x, the lower limit is a constant, and so the derivative is just the integrand evaluated at x. Similarly, in part B, to find h prime of x, I need to take the derivative of that integral expression. The lower limit is a constant, the upper limit is x, and so by the fundamental theorem of calculus part 1, the derivative is just the integrand evaluated at x. In this example, let's see if we can find the derivative of another integral expression, but this time notice that the upper limit is a function of x. In order to take the derivative of this expression, we need to use the chain rule. So we'll let u equal x cubed, and we'll start by taking the derivative of the outer function and working our way inside. We need to take the derivative of the outer function with respect to u, and then multiply by the derivative of the inner function, du dx. I can find the derivative of the outer function by using the fundamental theorem of calculus part 1. I need the derivative with respect to u, and notice that the upper bound on that integral expression is u, and the lower bound is a constant. So the derivative is just the integrand evaluated at u. And to finish this off, I still need to multiply by du dx. I did a couple of things in this last step. I substituted in the expression for u in terms of x, and I also found du dx, which was 3x squared. The fundamental theorem of calculus part 2 makes finding a definite integral much easier. It says that if f is continuous on the closed interval a to b, then the definite integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F is any antiderivative of little f, and that is, it's a function such that capital F prime is little f. Here's a closer look at the FTC part 2. Suppose we need to evaluate a definite integral a to b of little f of x. This theorem says that we don't need to use Riemann sums anymore. We just need to find an antiderivative capital F, and then we evaluate capital F at a and b, and we take the difference. I'd like to connect the FTC part 2 to particle motion. Suppose the velocity is given by a function v and the position by a function s. We know that v of t is the derivative of s prime of t. Early in an AP Calculus course, we often discover that for a particle moving in the positive direction, the area under the velocity curve is equal to the distance traveled. And in symbols, I could write that as the definite integral from a to b of v of t dt is s of b minus s of a. And that's just the fundamental theorem of calculus, part 2. Here are some examples which you can try. In each case, evaluate the definite integral and use the FTC part 2 if possible. The result in part A is pretty amazing, and I'd ask you to think about a geometric interpretation of that answer. And in part E, before you evaluate that definite integral, think about the assumptions necessary in order to use the fundamental theorem of calculus part 2. Now let's think about the fundamental theorem of calculus part 2 as telling us something about net change. We know that f prime of x represents the rate of change of y equal f of x with respect to x. And we know that f of b minus f of a is the change in y as x changes from a to b. But y doesn't have to be monotonic. It could, for example, increase and decrease and then increase again. So that means that the quantity f of b minus f of a is really the net change in y as x changes from a to b. So that means we can restate the FTC Part 2 in terms of this concept of net change. The definite integral of a rate of change f prime is the net change in the original function f. So the integral from a to b of f prime of x dx is just f of b minus f of a. Here are some interpretations of the FTC Part 2 and this idea of net change. First, the integral from a to b of f prime of x dx really represents an accumulation of the change in f over the interval a to b. And if I rearrange the terms in the net change theorem, I get an alternate interpretation and a very practical approach to many AP Calculus problems. So the end amount f of b is equal to the start amount f of a plus the net change, the definite integral from a to b of f prime of x dx. In this example, a cell phone battery with 500 milliampere hours of power is plugged into a charger, and the rate at which this battery increases in power is given by a function p, where t is measured in hours. Let's see if we can find the amount of power in the battery after 30 minutes. To solve these problems in context, I always look for keywords or key phrases. In this example, I have an initial amount of power in the battery, and I have a rate function. This is a good candidate for the fundamental theorem of calculus part 2 or the net change theorem. I'll let capital T represent the total amount of power in the cell phone battery at time little t, and then I'll use the net change theorem. I know that the end amount of power, capital T evaluated at 0.5, will be equal to the start amount, capital T of 0, plus the net change in power. I'll show you my technology solution in a minute, but I found that after 30 minutes, the battery had approximately 1480 milliampere hours of power. Here's how I used technology to solve this problem. Now please note that I could find the solution using one command line, but I like to separate out the steps on the way to the final answer. So first I defined the function p, and then I found the net change in power over the time interval 0 to 0.5, or half an hour. And finally, I added the initial amount of power to the net change for 1479.55. Here are a few more AP Calculus type questions concerning that cell phone battery. Let's suppose that while the cell phone is connected to the charger, at time t equal 0.3 hours, the phone is turned on, and it discharges power at a rate given by this function capital D. Is the amount of power in the cell phone battery increasing or decreasing at time t equal 1 hour? And make sure you give a reason for your answer. How much power is in the cell phone battery after 1.5 hours? And finally, find the maximum amount of power in the cell phone battery for t in the interval 0 to 2. I hope this video provides insight into the fundamental theorem of calculus and a few good problems for you to think about. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology, of course, but calculus and classroom activities, and lots of calculator tips and tricks for test success.